Come on guys, let's do this problems right here. The first question is asking if the electric flux through a closed surface is zero, the electric field at points on the surface must be zero. Is it true or false? So let's see what is the answer is going to be. So it's false because if the electric field is through a closed surface is zero, it means the charge enclosing the surface is zero. It doesn't mean that the electric field is zero, right? So that's the explanation. So for the answer for this one is going to be false. So electric field not necessarily have to be zero if the electric flux is zero, right? Let's look at the second one right here. In a certain region, the electric potential due to a charge distribution is given by the equation 3x square y square yc cube minus 2x c cube, where x, y, z are measured in meters and V is in volts. Calculate the magnitude of electric field. And we know that electric field is derivative of this volt electric potential. So if you find the derivative, that's going to be negative derivative, negative dV by dx. If you calculate negative dV by dx, that's going to give you the electric field. So let's see how we can calculate this one. So let's copy this one down first. So we have this 3x square. So let's raise equal to minus d over dx 3x square y square 3x square y square plus yc cube minus 2x z cube. So this is the one we are going to find. So let's calculate this one individually, like separating by x, y, z components. So let's take the x component first. If I take x component, only these two are going to come, right? This one right here and this one right here. So that's going to be minus 3x square. If you find the derivative, that's going to be 6xy square, and this is going to be minus 2z cube. So that's going to be the derivative, and if you add the negative, that's going to be minus 6xy square plus 2z cube. So let's go for the y component, ey. So ey is going to be only this one right here and this one. So if you find the derivative of that one, that's going to be 6x square y plus c cube. So this is the derivative of this one. So let's go for the z components. So that's going to be what? That's going to be ez equal to negative, and z components are this one and this one, right? That's going to be 3yz square minus 6xc square, right? So let's add the negative. So this is going to be minus 3yz square plus 6xc square, right? And here also we can add the negative. This is going to be equal to minus 6x square y minus z cube. Now here they have given that x, y, z are 1, 1, 1 at position 1, 1, 1. So if we substitute that value, that's going to give us the electric field in each components. So let's calculate the Ex first. So Ex, if you plug 1 for this xy, you will get minus 6 plus 2. That's equal to minus 4, right? And here we have, if you plug the values for y, we will get minus 6 minus 1. That's going to be equal to minus 7, right? And let's go to the third one. Third one we have minus 3. So minus 3 plus 6, that's going to be equal to 3, right? So now we have all the values. So finally we have to find the total net electric field. So net electric field is going to be simply square root of Ex square plus Ey square plus EZ square, right? EZ square, and if you square a negative value, you're going to get a positive value anyway. So let's write everything in terms of positive. First we have 4 square plus 7 square plus 3 square, and this is going to be equal to, and 4 square is 16, 16 plus 7 times 7, what is that? 49, right? 49 plus 9, and if you plug all this value in calculator and find the final value, that's going to give you 8.6 volts per meter, and that's the electric field due to this electric potential. And that's how we do these kind of problems. I hope you guys find this video helpful. Thanks for watching.